All right. Terminal voltage and internal resistance of batteries. Here we go. Let me turn on the light here so that you can kind of see it better. All right. All batteries have a internal voltage and internal resistance and a battery life measured in ampere hours, which really quickly, right, we know that 1 ampere is just saying one charge um, per second. Okay. So if we want to figure out what an ampere hour is equivalent to, then we just figure out, right? It's, 1 amp times seconds. So it would be one charge per second for an hour. Okay. For 1 hour, which is, oh, sorry, I guess I shouldn't say that right there. It should be something like, right? We know that for an hour is 360, or sorry, 3600 seconds, right? So to cancel out the seconds, right, then that gives you about or sorry, I guess it shouldn't say charge, it should say coulomb. Okay, coulomb. Again, that's the kind of notion that we use them kind of interchangeably, right? So this ends up being 3600 coulombs. Okay, okay. Well, terminal voltage is another thing that you have to understand, which is what a voltmeter, what a voltmeter reads if you connect it to both ends of the battery. So, for example, if you've been keeping up with our labs, you'll know that we took a 9-volt battery in one of the labs and we put the leads on either end of it, okay, and then we were able to figure out the voltage of the battery that way, okay. The terminal voltage is so what a voltmeter reads. Okay, if connected to terminals of a battery. Okay. If it's connected to the terminals of a battery, what is the voltmeter going to read? Okay. Um, Now you might notice if you did the lab with the 9-volt batteries that there is that the it says it had a 9-volt had 9 volts, right? But it actually read maybe less than that or maybe a little bit more than that. Okay. Because the terminal voltage is not just straight up what it says it is. There is an internal resistance that does affect the amount of voltage that actually leaves the battery, and we can figure that out by doing the terminal voltage is equal to epsilon minus IR. So the EMF of the battery minus the current going through the battery times the internal resistance of the battery. Okay, so terminal voltage is like the voltage that's actually leaving the battery, um, whereas EMF is kind of like the ideal voltage of the battery, right? Not all of that necessarily leaves the battery. Okay, so consider a battery with an EMF epsilon and internal resistance little r. It is attached to a variable resistor big R. Determine the following in terms of epsilon r and r. Okay, so first we need to figure out the current delivered to the battery by the resistor. And all we need to do is the easiest way to do this is to get equivalent resistance. So we do get equivalent resistance, okay, which gives you little r plus r, right? Because these two resistors are in series with each other, okay. And then part two, the second step that we need to follow is to get the current through the battery, okay. The current through the battery, again, if we call upon the pyramid of knowledge, okay, the current through the battery is going to be the EMF divided by the equivalent resistance. So the EMF, which is epsilon over R plus R, okay? And that should make sense because epsilon is our V, this is our resistance, right? Okay. Okay, terminal voltage V sub T of the battery. Okay, well, we know that V sub T is equal to epsilon minus the current through the battery times the internal resistance of the battery. And so we need to actually convert that into, we need to actually express that in terms of the things that we need to solve it for, right? So if it says determine the following in terms of these three things, right? then we want our answer to only be with those three things. So we're going to replace everything in here with other stuff that we've already done. Well, you should notice that, we already got I battery earlier, and it's this expression. So we're just going to plug that in there. Okay. And you should end up getting a new expression, V sub t equals epsilon minus epsilon over r plus r, okay, times r. Okay. Now, moving forward from there, all that we need to do is combine. Is first off, we want to we want to kind of simplify this as much as possible. So this is e minus, epsilon minus epsilon over r plus r times little r. Okay, so this would actually be epsilon r over r plus r. Okay, and you would notice. Okay, and you would notice that there's a similar term in both of these. So there's a similar something similar in both of these terms, and that is epsilon, right? So they both have epsilon. Okay, so it's going to be, if we factor out the epsilon, we get epsilon equals, or epsilon times 1 minus r over r plus r. Okay, now the last step that we need to follow is that we can simplify it still a little bit, right? If it's 1 minus this, and we can't subtract them unless they have a common denominator, then this would actually be true to say here, is that v sub t is equal to, again, epsilon outside, okay, but on the inside it would be r plus capital R over r plus capital R minus r over r plus capital R. Okay. Okay, now if we say that, then you'll notice they have this common denominator, right? Which means that we can start to cancel out stuff in the numerator, right? Little r minus r is still gonna give you 0, so we can cancel that out. Okay. And if you distribute the epsilon, you end up getting epsilon r over r plus big R. Okay, and that is actually the expression for the terminal voltage of the battery right there. Okay. Okay. Finally, the power P delivered to the resistor. Okay. So the amount of power that's delivered to the resistor is going to be defined by one of three equations, and we have to pick which one's going to work best. You can do P equals IV, you can do P equals V squared. I don't know if you can hear that like dinging. I don't know why my computer keeps connecting and reconnecting to something. Just ignore it. P equals I squared times R. Okay. Okay, the best equation to use here is going to be, in my opinion, at least this one, because it's going to probably look the nicest, right? And we got our I earlier, okay? And then R is also pretty easy to solve, okay? And this is talking specifically about the resistor, so we just want to find the values for specifically that resistor. Current's the same everywhere in the circuit, and then the resistance is given to us, right? So it's easiest to go with that one. So all we got to do is plug in our expression for I, which we got earlier, right? P equals epsilon over little r plus big R squared, and then R is just R because we are just given that for that. And so this ultimately ends up simplifying, right? If you square this fraction, it ultimately ends up simplifying to epsilon squared times R over R plus R squared. You don't have to like FOIL that out. This is perfectly fine right here. Okay, work smarter, not harder. Okay, the power delivered to R is maximized when R is equal to R. Okay, without referencing equations, explain quantitatively why less power is delivered to R if capital R is more than R. Okay, so if capital R is more than R, and it's hard to talk about this without referencing equations, right? That's because if less power is delivered to R, well, I'm thinking of this power equation that we just derived. I'm kind of not really follow the rules here and reference equations, but this equation that we derived right here, if big R is less than, or sorry, if big R is greater than little r, then we're affecting the numerator, but we're also affecting the denominator, and the denominator is what's being squared. And you can say the exact same thing, and you can say that pretty much the same thing for this too, is that it doesn't matter what happens, we are decreasing the power as long as we have in the denominator this r plus r squared because it's being squared, right? In the numerator, if we increase r, it'll increase too, but the bottom's going to increase faster because it's being squared, right? Either way, right, if we decrease r, we're decreasing our numerator, and we are decreasing down here, but still this is being squared, right? That's a pretty big change, okay? So I'm not going to write that in there. Okay? So the question that in the key actually was this was actually completely different. It just said figure out what the value of r will be to maximize p, and we would figure out that they should be equal to each other, because when the two r's are equal to each other, this becomes 2r squared, and then it actually cancels out with the r in the numerator so that you don't have that squared denominator, okay? Okay. Some students, I think, have this problem on their notes. Some students don't. I don't know why it's different. I might have accidentally printed two different documents, but it's kind of been a jumble. Okay. For this one, we're going to solve circuits just like normal. We're going to solve them, basically fill in the tables for them, and that should give us, what we're looking for. Okay, so starting out, we're given the values for each of the resistors. So this is 10 ohms, this is 20 ohms, this is 60 ohms. Okay. I drew those terribly. This is 50 volts. Okay. We need to figure out the current, voltage, and power through it all. Well, the first thing that we want to do is figure out the equivalent resistance. That's probably going to be our best bet, because then we can figure out the current from the battery, right? So Req equals, and I'm going to do this all in one step. You may not be able to, or you may not know how to. Okay. The way I'm doing this in one step is because it's just easier to do it that way. If you can train yourself to do that, it'll be quicker. 20 plus 1 over 60, okay, negative 1. Okay, remember, this is just combining the parallel into 1, and then this is accounting for the series, okay? So combine the parallel and then account for series, okay? And you should end up getting 25 ohms. Okay, so 25 ohms. I know it's X'd out, but that's the equivalent resistance of the whole thing. 25 ohms, okay? Then we can figure out that the current through the battery is going to be V over R, which will be 50 over 25, which gives you 2 amps. Okay, so that's 2 amps through the battery. Now, if it's 2 amps through the battery is in series with A, so it should also get 2 amps in there. Okay. Okay. B, or I guess moving on, right? We can figure out now that we have the two of our values for A, we can figure out the voltage drop through A, right? And that's just 2 times 10, which will be 20 volts. Now, from there, we can actually figure out the remaining parts and the remaining voltages, because we start out with 50 here, and then we lose 20, okay? 20 volts. We lose 20 there, and then between, no matter which way the current goes, whether it goes down or to the right, it has to lose the remaining of its voltage, right? Because there's only one resistor left for it to go. After it passes A, any one charge is only going to pass one resistor, so it needs to get rid of all of the remaining energy that it has. So if we start out with 50, we lose 20, we should have 30 left that's going to go to each of the resistors. Okay? And finally, the current through B, okay, the current through B, current through C, we can then just use Ohm's law, right? The voltage divided by the resistance. And for B, you should get 1.5 amps, and then for C, it's going to be 30 divided by 60, which is 0.5 amps. And this we can verify with Kirchhoff's laws, because, right, what it's saying is that through B, we get 1.5 amps, to C we get 0.5 amps. That adds up to the 2 amps that enter that junction. Okay, and then it'll add up back up to 2 amps at the bottom. Okay, to get the power, use your beloved equation P equals IV. Okay, and you just multiply everything through. Okay, I think you know how to use that equation, so I'm going to go kind of fast here. This is just 100 watts. This is 40 watts. This is 45 watts, and then this is 15 watts. And also as well, all of the power that you start, that all of the battery power should be dissipated. So 100 watts, right? These all should add up to 100. Okay, that's another way you can solve it. Okay, let's take a look at the next one. We've got a weird, funky circuit here. Okay, first and foremost, the easiest thing to do is to resolve it into a single circuit. And I'm actually going to draw out every step here because it's important for solving the remainder of the problem here in just a minute. Okay, so we're going to start out, we're going to get REQ. Always a great first step. Okay, if we're going to get the equivalent resistance, then what we need to do is we need to start combining our resistors, right? I can combine these because they're in series with each other, and then I can combine these because they're in parallel with each other. Okay, so we're going to go ahead and do that. And you should end up getting a new circuit that looks kind of like this. Okay. You should get a new circuit that looks like that. And then the left resistor, we're just adding A and B. That gives us 30 ohms. At resistor C, okay, we should get 80 ohms, because that's not changing. And then this other resistor right here, D and E combined, should give us 40 ohms. Okay. Then we do it again. Okay, we have to combine more resistors. Okay. So we can combine 80 and 40 to get a new single resistor. Okay. 30 ohms. You just add these two together, which should give you 120 ohms. Okay. Now, these values don't really mean too much to us right now. We're going to use them later to solve things. Okay. And then finally, we need to do one more thing to resolve it into truly one resistor, and that is actually going to be, 30 and 120 are in parallel with each other, so we can add them in a parallel fashion. So we should end up with this final circuit that looks kind of like this. Okay, and it should end up being 24 ohms. Okay, so the equivalent resistance is 24 ohms. Okay, good on us for figuring that out. Okay. Okay, now what we need to do is we need to figure out the total current in the circuit, which we can do Ohm's law. 12 divided by 24 should be 0.5 amps. Okay. 12 divided by 24 is 0.5, right? Okay. So then we can figure out, okay, from the battery, right? Well, the current is going to split off right at that first junction. So we can't really, there's nothing it's really in series with. We know that the current through A and B are going to be the same because they're in series with each other. Okay. Okay. But what we actually can do is we can go back to this step right here and to use Ohm's law and figure out how much current goes down the left side and how much current goes down the right side, right? This we can actually use for Ohm's law because we can figure out how much current is, at the junction, how much current is going to go left, how much is going to go right, right? So if we do, if we use Ohm's law for both sides, okay, and we get, for the left, okay, this is, 12 volts equals current through left times 30 ohms. Okay, ooh. Okay. And you can solve that for what it is, right? Because this is the total resistance of the left branch. This is the total EMF of the battery. And you should end up getting that there is about 0.4 amps going down the left branch, which means B and A are getting 0.4 amps. Okay. Now, you don't need to even do any math to figure out the next part because we need to figure out how much current goes down the right branch. Well, if you know that you had 0.5 amps and 4 of them go down the left branch, how many have to go down the right branch? It would have to be 0.1. Okay. So 0.1 amps go to the right, and they're all going to go through resistor C. C. 0.1 amps. That's a terrible color. Let's fix that. Okay, Okay, 0.1 amps. Okay. Okay. Now that we know the current through that, right, we can figure out the voltage drop through each one. Okay. And in doing so, all right. Oh, I already used purple. Let's use pink. Oh, I already used pink. Man, I don't have as many colors available to me at home. Okay. The next thing that we want to do is figure out the voltage drop across each resistor, right? All we got to do, 10 times 0.4 is 4 volts. 20 times 0.4 is 8 volts. Okay. 80 times 0.1 is 8 volts. Okay. Now, to solve the voltage through the remaining two resistors, D and E, we need to figure out how much voltage do we lose at C, right? Okay, so take a look at this, okay? If we're going to enter resistor C with all 12 of our volts, okay, and we're going to exit, we're going to lose 8 volts. We're going to exit with 4 volts, right? And doesn't matter, at this point in the path, okay, it's only going to encounter one more resistor. It's either going to go down the D path or the E path, okay? So at this point, all that needs to be done is, state that each of the resistors take the same amount of voltage from each other because they're in parallel, but they also need to take the remaining voltage. So D and E will take the remaining voltage, which would be 4 volts, okay? And then look at that. All you have to do is Ohm's law to get the current. Okay, you use Ohm's law, V over I. 4 divided by 50 gives you 0.08 amps. And then 4 divided by 20 gives you 0.02 amps. Okay. Now to get power, right? Remember, we're going to use P equals IV because that's the easiest one to use for this case. Okay. You should end up getting something like 6 watts. Okay, 1.6 watts, 3.2 watts, 0.8 watts, 0.32 watts, and 0.08 watts. Okay. Okay. All right. Okay, let's take a look at the next two. I believe these are the last two examples for this section. Okay. We have a battery. This one has internal resistance. This question down here that says terminal voltage of the battery, that actually applies to this question up here. It does not apply to the one below it, okay? So we figured out that the voltage, right, we know that the voltage of the battery is 10, and then we know the values for each of the resistances, okay? First course of action, always the best thing to do is start out by getting equivalent resistance, right? Req equals 5 plus 4 plus 1 over 20 plus 1 over 80. Okay. Okay. And that should give you, let's see, I didn't actually calculate it out in the key for whatever reason, but I can calculate it out right now. Okay. That should give you 5 plus 4 plus 1 over 20 plus 1 over 30, or sorry, 80. And we should get 25. Man, you notice a trend, right? 25 is the equivalent resistance for everything in this section. Okay. Okay. So now that we have that, we can figure out the total current going through the battery, right? V divided by R, which should be 0.4. Okay. Now, continuing through, right? The current so the current running through the battery is 0.4 amps. The current running through little r and A should also be 0.4 amps. Okay. Which means we can then solve for the voltage of those two. Okay. Which gives us, let's see, 5 times 0.4, that's 2 volts. And then 4 times 0.4, that's 1.6 volts. Okay. Okay, Doesn't matter, right? If when the charge is right here along its path, it's only going to go visit one more resistor, either B or C, right? So B or C need to take away the remaining voltage from the charge, which comes out to about 6.4 volts. Okay, right? 2 plus 1.6, or sorry, 10 minus 2 minus 1.6 is 6.4 volts, okay? And then we can work backwards to solve the current for each of those resistors. So we do voltage divided by resistance, and it is going to be weird numbers here, 0.32 amps, and then 0.08 amps, okay? Okay, and then finally we can calculate the power, okay, to figure out the power dissipated in this throughout the circuit. All we need to do is use P equals IV. Okay, I times V is going to give us 4 watts, so we should never exceed 4 watts around any loop. And then you should get 0.8 watts, you should get 0.64 watts, you should get 2.048 watts, okay, and then you get 0.512 watts, okay? I don't know why I wrote it out for those last two. I'm still pretty tired, okay? Now, terminal voltage, you can use the formula that we used, or you can take the EMF of the battery and subtract it from the voltage drop through the internal resistor. So, for example, this is our EMF of the battery. This is our voltage drop through our internal resistor. What is our terminal voltage? It would be 10 minus 2, which is 8, okay? Okay. The final question on here is a little bit more of a complex circuit. It looks complicated. It's really not that bad. Trust. Okay. This is a, it looks funky, but it's really not too bad, right? We're given the currents too here. We just don't know the resistance of resistor C now. So we're actually given a little bit more of a heads up. Something that's important to note is that, right, our current coming from 1 is 4. Okay. And our current coming from 2 is 2. Okay, so when they combine and they go into the junction, there should be a total of 6 amps because we add them together. Another thing you can point out is, right, if they have a current of 4 and 2 respectively, and that means that A and B are getting 4 and 2 also respectively, right? So A is getting 4 amps and B is getting 2 amps. Okay. Now, all we need to do is multiply to finish out Ohm's law here, okay? To finish out Ohm's law, okay, we do 5 times 4 is 20, and then 40 times 4, okay, which gives you 40. Okay, we still don't really know anything about C, well, except we actually do. We actually do know about what its current is going to be, right? It's going to be 6 amps. And there's nothing he can really do about that. We can really do about that, okay? Now, to get we still need to figure out the actual resistance and the voltage. It's probably not going to be a good way to get the resistance, but we can get the voltage from it, okay? But we can't get the voltage, right? If we use the loop rule, then we should know that if we use the loop rule, then we should know that R sub C should be compensating for the remaining amount of energy, right? Okay, so we only know the amount of energy that E1 gives out. So E1 is going to drop at R sub A is going to drop 20 volts, okay? And then at R sub C, it should get rid of the rest, okay? It should get rid of the rest. Now, that would mean that it would need to be 60 volts, or sorry, 60 ohms for the resistor, okay? Or sorry, 60 voltage drop through the resistor. Or through the resistor C, okay? So we should lose 60 there. Now, we can actually figure out the EMF of the battery now too, or sorry, of battery 2, because now we have a complete loop. At R sub B, we lose 40 volts, but then we also lose 60 here. So what's the total amount of voltage that EMF2 could have? It would have to be 100, right? Because, again, if you're going through B and losing 40, and then you go through C, lose some amount, end up at 0, it should be 100, Okay. Okay. And then finally, you can figure out the resistance of C using Ohm's law, right? If you use the pyramid, right? You can figure out that if voltage increases, then then resistance would decrease, or sorry, increase, right? The only thing that changes resistance in a negative way would be current, right? So V over R, that's 60 divided by 6, which gives you 10 ohms, okay? And the final thing to do is to calculate power, just like for everything else, okay? So then power is equal to I times V, which I'm going to write that over and over and over again, okay? 4 times 80 is 320, okay? And then 2 times 100 is 200, okay? And then you get 80, 80, and 360, okay? And this makes sense, right? Okay. All right. Well, that is solving problems with Kirchhoff's laws. Have fun.